Never really settled on whether it's afternoon or evening. Hello. It feels like nap time. My eyes are burning. You know what that means. Been awake too long. I'm recording. Don't tell the world that. I made a couple extras, so maybe today we'll have a chance to get more out to you guys to look at. Did any of you buy a modeling kit before or for this class? Great. Lean into it in section 3, 4, and 5. That, I would say, is when it is the most useful. After section 5, it kind of stops becoming useful. And in OCHEM 2, it's not incredibly useful. So take advantage of it, because this is the time to use a modeling kit. And those of you that don't have a modeling kit, where can you find one for free? Not to keep, but to use for free. STEM Center, always at the STEM Center. I ran into Peter on my way into class, doing his homework, which is great. Did I move that due date? Okay, that's on Friday. Sunday, because you're not going to do it until Sunday anyway. Did I move both of them? Okay, that's great. Thank you. Huh? That's fine. I will take the PLO until the final exam. But the most useful point of the PLO is right about now while you're learning it. So I want it on your radar. That's why I have the PLO due this week. But I will take PLO assignments until the final. I'll change their due date eventually so that they come back on your radar, because they're still useful exercises before the final. So I ran into Peter doing his homework, and I want to say he had, I don't even know really, a structure that looked like this. Oh, you know what? There's some geometry in there that I'm not a big fan of. So I'm going to just start over. I don't know if I can remember exactly the right one, so I'm going to take a different stab at it. Let's look at this compound. No, I didn't go far enough. Let's look at this compound. There are two ways to name this that get the exact same carbon chain. And this was a rule I forgot to mention in nomenclature. I promise you, I don't test on it because it's an interesting rule, but it's just not one of the most common, and I'd rather you master the most important rules, like lowest locant set, prioritize functional groups, alphabetize the substituents. But this is an interesting one. Let's see if I did it right. 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. Two parent chains, different substituents on the two of them. So that makes an impact on how you would name it, correct? Both would have the root heptane, root and suffix, but one of them, this route, would have a methyl group and a propyl group as a substituent, whereas the other route has just this group. Could you name that group as a substituent? Feel free to use your notes. What family is it in based on the number of carbons in the substituent? Airplane shadow. Did you guys see that? That's cool. This is sec-butyl. It's definitely a butyl member because it's got 4 carbons in the chain. And it's attached at that secondary carbon, which is actually a tertiary carbon. But if it weren't attached to the parent chain, it would be a secondary carbon. Gotta love the confusion in that. You could also call it 1-propyl or 1-methyl propyl. Yeah? Because it's a 3-carbon chain with a 1-carbon substituent off of it. So which way is better? To take heptane that has 3-methyl-4-propyl substituents, or to take heptane that has 4-sec-butyl, one substituent. Without deciding what the actual rule is, what do you like better? You like one substituent? Fewer substituents? Go for the name that has fewer? Anybody disagree? Anybody agree? Yeah? The rest of you just feel so indifferent about it. Couldn't care less. The rule is maximize substituents. When you have two identical parent chains possible, choose the parent chain with the most substituents. So the correct name here is 3-methyl-4-propyl heptane. Even though the exact same structure is drawn if you drew 4-sec-butyl heptane. We choose to maximize substituents. With equal parents possible, maximize substituents. How often are you going to see this on a unit test or exam? Probably never. When will you run into this in real life? Maybe never. So I wanted to point it out because it is on your homework. And that's when you'll run into it. Okay. Today we're going to talk more about stereochemistry. In stereochemistry, molecular projections are an important thing. These are ways that we view molecules. We're going to talk about 3 different ways to visualize molecules, and we're only going to really lean into one of them as the most useful form for us. I'm going to move my notes over here so that I can use the screen. The first one that I want to talk to you about is called the sawhorse projection. How many of you have used a sawhorse? Yeah? What's it used for, Elliot? Yeah? You cut it? Yeah. And they call it that because it looks like, kind of looks like a horse, I guess. Yeah, it depends on how many horses you've seen in your life. But a sawhorse is a workshop piece of equipment. It's got those 2 legs on either side and then a bar in between them. This is the sawhorse projection. I wanted that to be big. This is the sawhorse projection in stereochemistry. Here's your zigzag of your molecule. The sawhorse highlights one of these bonds. It exaggerates a carbon-carbon bond. And then it kind of flattens these other 3 groups. So you'll see here that this bond is exaggerated, and then these other 3 groups are just flat. This is what you guys were working on at the end of Monday's class. Taking a molecule and drawing its 3D projection with wedges and dashes. The only difference now is that you're taking that molecule and you are picking one of these bonds to exaggerate down and then showing these other 3 groups just coming off of it. I'm going to be honest, I don't like this projection very much. Because if you don't draw it well, it doesn't have a lot of meaning. It doesn't convey a lot of things. But there is some assumed perspective here. I'm going to write that out because it's not a vocab term, but it's something that I lean into a lot. Does assumed have two M's? Okay, thank you. Assumed perspective. What perspective are we assuming? Well, we're assuming that this that this carbon group here is in the front, and that this is in the back. Correct? And we're assuming that this is three-dimensional, stretched this way. We're assuming that this is tetrahedral, but it's flattened. So we have some assumed perspective in this. We're taking out all of the wedges and dash information, and we're flattening it. But you can't assume that this is in the back and that this is coming towards you. That's the wrong perspective. We're not going to use it much because I don't like it. But you will see it occasionally from time to time. It's not also that I just don't like it. I have yet to understand its purpose. I don't understand why it's useful. I've not seen somebody present information about a molecule through its sawhorse information in a way that conveys more meaning than some of our other projections. So that's the main reason we're not going to do it. The next one that I want to just touch on is called the Fisher projection. I need to check quick. I might have spelled Fisher inappropriately. No, I spelled it correctly. The Fisher projection, named after a fish, of course. The Fisher projection also has some assumed geometry. This creates a fish backbone of carbon. I don't know if you've ever taken a fish's backbone, but oftentimes it has this slight bow to it. And that's how we're going to take the backbone of carbon in a Fisher projection. We're going to line them all up. No zigzags. All zig-zigs. So, looking at this structure, here's that zigzag. Here's that wedge dash, wedge dash, wedge dash. We learned on Monday that if I take this carbon and I take its zigzag and I turn it into a zig-zig, that the wedged H becomes what? A dashed H. And the dashed OH becomes a wedged OH. And if I don't change the vertex, then the wedges and dashes don't change. If I don't change the vertex, the wedges and dashes don't change. If I change this vertex, my wedges and dashes invert. So with the Fisher projection, you take a zigzag bond line and you flip every other one of them so that they're all oriented the same way. And you can kind of see this curved backbone. The reason I'm not giving you a handout with all of this, or even like expecting you guys to draw most of this down, I'm going to give you some information up there that's smaller, is because we're not going to use this much either. But if you go on to OChem 2 at some places, you'll need to know this. Not necessarily here so much. And if you go on to biochemistry, they use Fisher projections a lot. Fisher projections are really big in sugars. This is a sugar, a linear form of a sugar. Now, you take this backbone and you sight down it. You assume a perspective where all of the carbons take this straight line. And because it bows out, when you're looking at it, all of the carbons are pointing away from you. And all of these groups are now all coming towards you. So I want you to imagine, this is a three-dimensional thing. I am setting myself in the plane of the board. This OH is out here. The hydrogen is back. And as I twist this out, they're both coming towards me. This is art class. Really, you have to understand perspective of the three-dimensional molecules in this unit in order to do well. So let's simplify it. Fish backbone. I'm going to take just a 4-carbon chain. I'm going to put an OH here and an OH here. We're going to first take out all the zigzags and make them zigzags. Any vertexes that we don't change, their stereochemistry, their wedges and dashes stay the same. Any vertexes that I invert, their stereochemistries flip. My dashed OH becomes a wedged OH. You guys tracking? Similar to what you're doing? I've got this small molecule, so if you want to take the structure that is in front of you, feel free to rotate it so that you can see that. Pick one of them to pretend to be that OH. Then we take this assumed perspective. I'm going to draw it down here. And because we've got this smaller molecule, I can actually say, imagine that this bond is the plane of the board. It's flat. There's a CH3 that goes away from it on either side. And then there's these 2 wedged groups on either side. I want you guys to take a second, and I'm gonna give you the perspective. Just like this, if you were to sight like this, you know what that is? Eyeball. Put your eyeball here. Where do the OHs go? What are the other groups that take up the other dashes, wedges? Try to take 15 seconds. Put yourself in the plane of the board. Figure out where the OHs go. Feel free to use those models if you want to. And twist them as you need to. Line it up to that. Put yourself in that perspective. You doing it in your head? Is that your guess? I would encourage have these dashes right now, and have both wedges. Fill in the other wedges with hydrogens. Hydrogens. Yeah, because they are hydrogens. Where we've got the wedged OH, there's a dashed group, but it's not shown. What is the only thing we assume? There's a dash. If it was a C, wouldn't it have to be a CH3? If it was a CH3, it'd have to show a line to it somehow. Then you guys have different answers, so I want you to talk about what you're seeing. You got the whole thing copied up, except for mine. You what? Yeah? Put your head here. What's coming out towards you? The OH. Now you got to twist it like this. Yep. Since they're on the same side, then they should be on the same side of the Fisher projection. All right, so are you ready? Do this with me. And I mean this. It's okay to do this. Put your head down with it. What's coming out? OH. What's going back? H. You remember how every tetrahedral carbon has two in-plane bonds? One wedged, one dashed. Why is there no dashed bond here? It's assumed. We don't have to draw in all those hydrogens. But there is a dashed bond. Here's in plane, here's in plane. There's a dashed H. There's a dashed H. Why is the H not dashed here? Because it's wedged. And then we flipped it. And the wedged H became a dashed H. So put your head in here. What's coming out of the board? OH. What's going through the board? H. Grab onto it like you're holding onto a steering wheel of a pirate ship. Pull it out. Flatten it. What do you get? OHs are on this side. I don't think I saw anybody move their hands. But I mean it. Use your hands. Make it 3D because you are working on a two-dimensional medium representing three-dimensional structures. OH, OH, H, H. If you leave the wedges alone, that assumes they're CH3s. You got to draw on the H's. Both of these H's are coming up. Sorry, both of these OHs are coming up. So you should think of them as being on the same side at the end. But this is not how they represent Fisher structures, Fisher projections. They're too messy. There's too much going on. So again, assumed perspective, they assume that you recognize the carbon bone is curved away from you and that all of these other groups are coming towards you. So now that we are under that assumption, here's our structure. How much information is in that, that structure there? A lot. There's a lot of spatial information in that structure. And most of it is assumed. It's assumed in the perspective. If I didn't tell you, how would you have known? If you look at this sugar in its Fisher projection, it just kind of looks random. I don't know why those OHs switch every so often and sometimes don't switch sides. I don't know what it's saying. It's saying this, which is actually this, which looks more like this in a regular bond line structure. There's a lot of assumed perspective there. Yeah? All right. The last perspective that we use very often, and this is the one that you'll have on your unit tests, on your exams, is the Newman projection. Would you believe that only one of these is not named after a man? Sawhorse is the only one. If you can come up with better ones, I'll take it. Honestly, the Fisher projection, I would have called the fishbone projection instead. I like that name. It's just coincidental that it kind of lines up. Newman projection, I don't know. I haven't figured out what I would have named it if I were Newman. But what we're going to do here is cite down a carbon-carbon bond. So I want you guys to work with the structures you have in front of you. We're going to cite down the center two carbons, but you can draw Newman projections along any carbon-carbon bond. When we take this, and I'm gonna stay with my molecule with these two OHs. When we put our eyeball in the plane of the board and we look at it, here's the bond that I want to cite down, that center carbon-carbon bond. And actually, I want to bring you somewhere where you can practice this on your own. On our homepage, in the external resources, there's this website that I used a lot in inorganic chemistry. It's called SimOtter. This link to SimOtter. You need to change from point group to molecule type so that you can look under these organic molecules. And I will say there's not a ton of molecules on here that work super well, but it does work. So you get this three-dimensional molecule. So this is what we're looking at. Actually, I guess it's more like this. This is what we're looking at up there on the right, more or less. CH3, OH forward, CH3, OH backwards. When I take my perspective and I look this way, here's what I get. That's our Newman projection, sighting down the carbon-carbon bond. You'll notice that you can't easily see the carbon in the back. And you can kind of see which carbons are coming from the front and which ones are coming from the back. If you're looking at the detail enough, you can actually see like the curvature here. So we need a way to more easily represent this. So we're going to do a big circle with a dot in the middle. Which one is the back? The big circle is the back, which is almost exactly opposite of this, right? Here you can't see the back. We want to clearly distinguish what comes from the back, what comes from the front. So we make the back really big. Then, looking at this group, I've got a CH3 that goes up. I've got an OH that goes in and an H that comes out. So I'm grabbing onto them like my steering wheel, and I'm pulling them out, and I'm putting them in. I have a CH3 that goes straight up. Down to my right is OH. Down to my left is H. And I have to say, they are specific placements. I can't just say, oh, the OH or the H can go either way. These are specific. When you put your eye in the plane of the board, that's what you see. What do you see from the back? And this is set up to model that, but with different atoms. So if you can imagine what you'd be seeing there, and then try to confirm it by what you see here, do that. Take your models. Put them in that zigzag formation. Sight down your carbon-carbon bond. I want you to draw what you see. Most of you have pencil, right? You can erase it. It's not on the front carbon. Is that right? Do you agree? That's a good question. Where is the other OH? You're going to draw it. Great. Sure. It's on the back carbon. The circle. On my front carbon? No. This is not exactly what's up there. This is actually the anterior of what you have up there. So I can't make it happen, but this is coming towards you. My OH is going away. So when you look this way, this is on your left, so mine should be on the right. You agree? Are you holding that model? Pass it around. Make sure that everybody can sight down that model. Look down it. What do you see? You see these groups coming off of it. straight down, straight up, down to the left, down to the right, up to the left, up to the right. When I draw something connected to the back carbon, I start at the circle. That's the benefit. I can clearly tell what goes to the front carbon because it goes all the way in. And I can clearly tell what comes off of the back carbon because it starts at the circle. So if you drew from the back carbon, but you drew it all the way in, just erase those lines so that they start there. When you put your perspective here with your model, you should see a CH3 group that's coming straight down off the back carbon. Where's the OH? Top left. It's wedged, so when I grab onto it and I straighten it out, it's on my left-hand side. Here's another thing that I want you to take away from this exercise. The OHs have different stereochemistry. One is wedged, one is dashed. You agree? That reflects in the Newman projection. We can call groups that are pointed towards us as being up, out of the plane, towards you. And things that are dashed, going away from us, we can call them down, out of the plane, away from you. Things that are up will always show up on one side of the Newman projection. Things that are down will always show up on the other. A down OH, an up OH, they show up on opposite sides. Up OH, up H, they show up on the same side. I'm not trying to say that up is always on the left and down is always on the right, because we could have taken our perspective and we could have drawn it from here. And we would have said that now this group is on the right-hand side. So I want you to do that next. Take this same structure, draw its Newman projection sighted down, the same carbon-carbon bond from the opposite direction. See what you notice. What changes? Does anything stay the same? Feel free to collaborate with each other. Talk with one another. What are you seeing? What are you not seeing? is there an assumed perspective? Kind of. We're flattening this tetrahedral carbon. These groups are actually all pointing towards you, but we just draw them flat because it's easier to draw. Good. 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 Okay, so the only thing I would change here is, sorry, is this your new one or your last one? Okay, sorry. Well, it's going to be different, guys, because when we cite from this side, the front carbon here has a CH3 group that's pointed down in space. But you still have a line that's going straight up. That front carbon, when we look from the left, it's got a CH3 group that's literally pointed down. It's pointed down at an angle, but it's not pointed up. Right? So the front carbon, the dots, should have the peace sign, the line coming straight down. The back carbon is inverted. Great job. Yes.
So can you do this with 4 carbon chains?
No.
Oh, okay. So I was gonna say, I'm sure it gets.
Oh, you would just
You know what I mean?
you would just abbreviate the rest of the structure,
Okay.
or like draw it in, but you wouldn't be citing down multiple bonds.
That's what I was.
Yeah.
So you're not gonna.
So the shortest molecule is 2 carbon chains.
Okay. Oh, sure.
But as long as you have 2 carbons next to each other, you can cite down them and draw the rest of the structure.
Okay.
Good. Great job. Okay. What you should have seen with this is that your front carbon now has the CH3 that is straight down instead of the back carbon. So I want you guys to get familiar with some common shapes. You're going to get these peace signs in here. Nice triangle on the front, nice triangle on the back. Now it's the back carbon that has a CH3 that's going up. And I want to show you guys what I see. This carbon has a CH3 group that is literally pointing down on the board. Not straight down, but that's what we're changing in our perspective. It is pointing down. It's not pointing up. That's what the back carbon has. It has a group that is pointing up. So if you see a group pointing down, it's going to point down in the Newman projection. If you see a group pointing up, it's going to be pointing up in the Newman projection. Yeah? The OH, it's coming out. The H is back. As I flatten it, OH is on my right-hand side. I don't even need to do the work for the back carbon. This is up towards me. This is down away from me. Is the other way OH going to be here? No. It's here. Okay? Now this type of Newman projection, where you have alternating groups, where the groups on the front carbon are staggered from the groups on the back carbon, we call this staggered. And this is usually where the class really starts to hear my Midwest accent. I think you guys heard it Monday because I was saying zag a lot. And I think maybe some of you didn't know what I was saying. Zigzag, staggered. You can call it zig. I don't know how you guys say it. Zigzag, zigzag, staggered. You can call it staggered if you want. I call it staggered, and you understand it, right? The groups on the front are offset from the groups on the back. The other type of Newman conformation that we have is called eclipse. in an eclipsed conformation, the groups on the front are lined up with the groups on the back. You'll notice I've only drawn the groups on the front so far. If we actually eclipsed them, we wouldn't see the groups on the back. So we need to be a little bit creative about how we show them so that we can draw them and still show that they're not staggered. So just to the side of each of these groups, we're going to draw the other set. More often than not, you can very easily tell when it's not staggered. Those might not look perfectly in line or parallel or eclipsed, but they're definitely not staggered. Would you agree? They're not this beautiful Y intercepting an upside down Y. Yeah? So I want you guys now to actually work a little bit backwards. I want you to take a staggered conformation for this molecule. And I want you to draw it in its bond line form. I just need to make sure that I actually draw the molecule and don't screw it up. And what I'll give you as a hint is that you're allowed to, there's two ways that you can draw it. There's a lot of ways that you can draw it, but I would recommend you draw this as a zig-zig bond line. Zig, zig. Yeah? So make your carbon chain in plane. It's not zigzag. Notice that this is zigzag and my carbons zigzag. Here, my carbons actually come back on each other. Zig, zig. And then figure out how you want to draw the hydrogens. That could mean you're taking it and you're laying it flat this way, or you're taking it and you're laying it flat this way. Figure out how you want your OHs and your H's drawn. Use the models in front of you and use them as kind of a comparison of where groups are going to go when you take it from Newman back to bond line. No. Draw the eclipsed structure in its bond line form. So like the structure on the top, but it's not zigzag. This one is zig-zag. Yes. But your OHs are on the same side. Yeah. So they need to be on the same side. Well, this is saying that the OHs are on the same carbon. One is on the front, one is on the back. Yes. Beautiful. Great job. Perfect. Well done. Nailed it. Now I want you guys to look with Natalie because it's a little bit different. I want you to see if you can find the similarity and the difference between them all.
Sorry. Oh, okay. In the back. Yeah.
I would keep these T3s in place. Yeah.
Zigzag?
Just like that. Which means this now has a wedge in the back, and this has a wedge in the back. Yeah. Good. Stick with that. Great. Good. Good. Zig zig. Zig zig. I know I don't say it well because they sound very similar. But this one, you can see how the carbons come down, over, and back up. Unlike the top one where it comes down, over, down, right? Down over down, zigzag. Down over up, zigzag. Good start, dude. Good start, Sarah. But now you need to show stereochemistry. Nailed it. That's it. That's it. Great job. Up to you. Oh, I was like, what are you looking for? What you got? Yes. 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 I want you guys to compare with Will's. Will's is different than all of yours and still correct. Well done. Anybody feeling brave enough to draw theirs up here?
I'll draw it.
Yeah, come on up. Is it easy to count the number of carbons in a Newman projection? Once you think about it, it is. That dot is one carbon and the circle is the second. So you can say 1, 2, 3, 4. But you've got to count on that Newman projection. Yeah? After that, it's easy. Which means I could give you a molecule in Newman projection and ask for you to name it. Because it's not impossible to convert it from Newman back to bond line, but you wouldn't even need to. You could just count straight through the Newman projection. Great work. All right, class. Did Will take his Newman projection and lay it down to the left or lay it down to the right? To the right? To the left? To the left? Peter, you want to defend? Yeah. If it's to the right, then these hydrogens will come to you. And his hydrogens are not. If it's to the left, flip it like this, then the hydrogens go away. Are the hydrogens, I keep saying hydrogens and I mean OHs, the alcohols. Are the alcohols on the same side of the Newman projection? Yes. Last time they were not. The alcohols in this staggered conformation were on opposite sides of the Newman projection because they had opposite stereochemistry. Now, they are on the same side of the Newman projection. They have the same stereochemistry. How cool is that? Cool. Newman projection is going to be our biggest hitter when it comes to stereochemistry. And now, we need to talk about energy strains. There are two types. The first and the strongest is called torsional strain. Does anybody know what torsional means? Twisting. How do you know that?
Medical stuff.
Medical what? Do you want me to say it? Testicular torsion. This is a good way to remember it, all of you medicine people. Testicular torsion is when the testicles twist. Also causes an energy strain. We say that a molecule has torsional strain as it rotates. That's where we get the name torsional from. I would have maybe called it something else because you can imagine a structure in a position that has torsional strain without thinking about how it rotates. But as this molecule rotates around, these bonding pairs of electrons become eclipsed. Eclipsed. And what do bonding pairs of electrons do they repel. Torsional strain is bonding pair of electron strain. Electron pair repulsion. This only appears in eclipsed conformations. If you have a staggered conformation, you do not experience any torsional strain. You have no eclipsed groups, no eclipsed bonds. Prove it for yourself. Rotate your molecule. Every time it becomes eclipsed, the bonding pairs are eclipsed, torsional strain. Every time it becomes staggered, there's no eclipsed bonding pairs, no torsional strain. The second type of strain is called steric strain. And steric comes from the same word for stereo. Spatial. This is spatial strain. Do you know what makes up this, what takes up the space that we call an atom? What makes up most of an atom's size? The electron cloud. So steric strain is a competition for space between these groups. You hear that? That's groups competing for space. They're running into each other. And falling off. If steric strain is this competition for space between groups, and the space that these groups take up is just electrons, then this is just another example of electron repulsion. Maybe a little bit less about electron pairs and a little bit more about the space that electrons take up, but this is just electron repulsion. But I like to think of it as fight for physical space. Steric strain shows up in two ways, but there is an important caveat about steric strain. Hydrogen never experiences or causes steric strain. I'm just abbreviating that with sterics. Hydrogen is not responsible for sterics. Hydrogen in and of itself. Hydrogen fighting for space with hydrogen, or hydrogen fighting for space with bromine, or methyl, or phenyl. But a CH3, something that has hydrogen, that can fight for space with a CH3. Yeah? It's hydrogen alone doesn't cause this steric strain. Hydrogen is not responsible for sterics. So there's two instances that we see this happen. We have eclipsed sterics. In this eclipse structure that we had before, we have OH eclipsed with OH. That is steric strain. They're fighting for space. And you can see it. Put them into this eclipsed conformation and look at how your groups get much closer to each other than the hydrogens do. They're much bigger. They take up more space. They cause strain by repelling each other. There's another steric strain. It's the overlap of what? Sorry? The methyls. CH3 to CH3. Those H groups don't experience steric strain. This is not the only eclipsed conformation of this molecule. I'm going to show you another eclipsed conformation. In this one, I'm going to keep the front carbon the same. CH3 up, OH to the left, H to the right. But I'm going to rotate the back carbon by 120 degrees. I'm going to rotate it clockwise. I could rotate it any way I'd like to. I'm going to rotate it clockwise. OH rotates to the top, CH3 to the bottom right, and H to the left. How much steric strain does this molecule experience in this conformation? Less, because it's just the eclipse of methyl with OH. My non-H groups. They're not hydrogen, they're other things. They experience steric strain. Why does this not experience steric strain? Hydrogen won't cause that. And why does this not experience steric strain? Hydrogen won't experience steric strain. So steric strain is the result of eclipsed non-H groups. You could say eclipsed non-H groups. I do hear students get confusion and they're like, CH3 has an H, OH has an H. Aren't those H groups? No, I mean like they're not hydrogen groups. They are something other than hydrogen. Making sense so far? And you had a great point there, which was this has more strain. This has less strain. Yeah, John. More strain, less strain. These are the same molecule. They're just at different points of rotation, different points of torsion. And they're experiencing different strains. Not every conformation experiences the same amount of energy strain. This, we say, is higher energy. This is lower energy. More strained, more energy. Less strain, less energy. How would you describe stability? Which of these is more stable? On the right? The less strained one? Where does my pen have more stability? Up here or up here? Technically down here, right? It's lost a lot of its potential energy. It's more stable because it can't fall anymore if somebody knocks into it. Less stable, more stable. I want you to know how these terms relate to each other. How does stability relate to strain, relate to energy? The other way that we see sterics is in staggered gauche interactions. Anybody know gauche? You do? From what? Your grandma said it. Is she French? She hated if people sat incorrectly? Like elbows on the table? Well, she taught you well, Peter. How gauche. How gauche of you. And that's what she would say. You're being very gauche. Anybody else know gauche? Where do you know it from, Elliot?
Yeah, my parents.
Your parents would call you gauche too?
No, not me.
Oh. Other people. When they're doing what? What do they call them gauche for?
Instead of like tacky, like
Sure. I want to say gauche comes from the French for awkward, not cool, don't do that. And so I kind of have this vision in my head of gauche being like sitting in between people on an airplane. Like, this is so uncomfortable. I don't like this. And that's what gauche means here. If you have a staggered conformation, I'm going to go back to our very first conformation where I have CH3 up, CH3 down. On the back carbon, OH is to the left. On the right carbon, OH is to the right. Does this molecule experience torsional strain? No. It does not have eclipsed bonding pairs. So those bonding pairs of electrons are not repelling each other like magnets. No torsional strain. This only happens in eclipsed conformations, and this is staggered. And none of those hydrogens are going to cause steric strain. Instead, this CH3 group is butting up against this OH. So if you have your conformations, or if you have your molecules, you can put them into your zigzag, your your staggered conformation, and then you can look at how these two groups here, one that's up to the side and one that's straight up, they might not look like they're fighting for space, but they're not as far away from each other as they could be. They are starting to impede on each other's space. That's the gauche interaction, and you can see it well by drawing these lines. Now, I don't know exactly what these lines are. This is kind of common to see drawn. I like to think of it as drawing their rough size. Yeah, because we're writing letters, but we're not showing the size of the groups. So this is butting up against this. That's a steric strain. It's not as much steric strain as they have when they're fully eclipsed, but they're still pushing away. They'd like to be further away. Is there more steric strain in this molecule? Same thing on the other side. Gauche, CH3, and OH. Gauche is when two groups on opposing carbons, front and back, are next to each other. True or false? Two groups on the same carbon will never have gauche steric strain with each other. True. Gauche steric strain only occurs between a group on the front and a group on the back. They've got to be on opposite carbons to be able to cause steric strain. I'm going to draw another staggered conformation of this molecule. I'm going to keep the front carbon the same. That means CH3 straight up, OH to the right, H to the left. This is still staggered, so my back carbon is still kind of this opposite structure. But I'm going to rotate it counterclockwise so that the CH3 moves to where the H is. H moves to where the OH. OH moves to the CH3. CH3 to the right, H to the left, OH to the bottom. Do you agree? 120-degree rotation. Each group swaps around. Is there more steric strain or less? Why don't you get this copied down? Work with your tables. Try to identify all of the steric strain that you see from gauche interactions. Am I saying gauche right? Those of you whose parents called you? I mean, other people. I used to call it gauche, and then I learned. You can call it that. Just don't tell the French. question?
Like if they're the same molecule, does that more problematic than the other confirmation? That's what
These are all the same molecule. All four of these.
No, yeah, they're all the same. I'm just like, is the molecule, sorry, not the molecule. Are the groups being the same causing more?
That's a good question. There are calculations of how much steric strain each group has with other groups.
Okay.
We're not going to get into it.
Yeah.
If it's not hydrogen, it causes steric strain. We are going to talk about relative size, but I'll tell you which ones to think about as bigger and which ones to think about as smaller. Okay?
I'm immediately looking
That's what I'm wondering. That's
slightly bigger than carbon.
No, it's not. Oxygen is a smaller nucleus. Not nucleus. It has a higher effective nuclear charge. Oxygen is a smaller atom. It pulls on the valence electrons stronger. Beyond that, OH has less atoms than CH3. CH3 takes up more space as well. But it's a good question. Do the groups matter? Here, it actually doesn't. What'd you find out? How much steric strain in this new conformation? 2, like we had before? Less? Less? How many? Just 1 steric strain? Where do you see it, Peter? OH to OH. These are gauche to each other. Anybody see more?
The methyls?
Methyl to methyl. They're gauche to each other. They're on opposing carbons. And they're adjacent in the staggered conformation. Good. Anything else?
Do the methyl and the alcohol on the right also experience like in a...
Yes. They're on opposing carbons, and they're gauche to each other. They're adjacent to each other. That this OH and this CH3, they're experiencing steric strain on both sides. So how much steric strain? 1, 2, 3. Which of these conformations has more strain? The second one. More strain. Which of these is more stable? The one on the left. More stable. Which of these 4 conformations do you think the molecule spends the most time in? Keep in mind that molecules move really fast. Air molecules move at like 300 meters per second. That's the speed of sound. They are bumping into each other incredibly fast. Liquid molecules, a little less fast, which is why sound travels slower but better in liquids. But as a molecule is moving, and like Aiden and I demonstrated the other day, as it's moving and running into things and twisting, which of these conformations do you think it finds itself in the greatest percentage of time? We can call it 1, 2, 3, 4. You said 4. You said 3. Why don't I put the numbers so we can... By the way, every molecule has 6 conformations. Not all of them are unique. There are 2 conformations missing. One of them is the same as this, but it's the other CH3 and the other OH that eclipse. And they have another staggered conformation, but it's the same as this, where everything is on this other side. Which of these conformations do you think the molecule finds itself in the most? How would you guess? Huh? Stability. An energy well. That's where it's going to find itself in the most, because it's going to need to get bumped up higher in energy to go to another conformation. So which of these four is the most stable? Number 2, the eclipsed on the right. Number 3, the staggered on the left. Raise your hand for 2, about half the class, maybe more. Raise your hand for 3. Yeah, that's less than half the class. What are you basing it on? The amount of steric strain. Yeah? This has 2 steric strains, this has 1, but this also has torsional strain. Torsional strain is stronger than steric strain. It's that repelling of eclipse bonds, so they really want to offset each other. Did I bring in my magnets and I had you guys feel them? Do you remember trying to push those magnets next to each other? What did they do? They slipped. Every time you got them close, they slipped to the side. This is that magnet. You want to get them close, they're going to slip to the side. You want to put it into an eclipse conformation, it's going to slip to the side. That's where it's more stable. Here's the rule on these Fisher projections. Goddamn. Here's the rule on these Newman projections. All eclipse are higher in energy than all staggered. I bet you could find a molecule that proves me wrong on that, but 99% of the time, that is always true. Eclipse is always higher than staggered. So what's our most stable conformation? It has to be one of the staggered groups, and it's going to be the one with less steric strain. So 3 is more stable. I'm going to rank this by more stable. What comes next? Sorry? The other staggered conformation. What's the next most stable on our way to the least stable? 2. Because now it does have steric strain, but it has, now it has torsional strain, but it has the least amount of steric strain out of the groups with torsional strain. You will see in your textbook, in all textbooks, that they will plot this energy. And they'll say that it goes from low to high, to intermediate, to higher. These strong peaks are always eclipsed conformations. They're basically transitioning between staggered conformations. Imagine setting a marble up here. It's always going to roll to one side or the other. Your eclipsed conformations are always going to fall to one staggered or the other. These valleys are the staggered conformations, but not all of them are of equal energy. Some are more preferential. Great work, guys. Let's take a break. Why don't you get up and move around and get your blood flowing?
How many classes do you have per year? They're spread. I totally get that.
I've heard a lot of different opinions on that. Some people in college would say if you did well in OChem 1, you would not do well in OChem 2. But if you didn't do well in OChem 1, you'd do really well in OChem 2. They are different beasts. Look at how much time we're spending right now just looking at molecules. You don't spend any time looking at a molecule in OChem 2. We're going to spend the last half of our semester looking at reactions. All of OChem 2 is reactions. So if you are good at pattern recognition, OChem 2 comes really easily to you because you just need to remember the reagents, the functional groups, and what the products are. And then also how they work. In OChem 1, it's just so much more broad. You need to know those things for a smaller set of reactions. You also need to know all this terminology. You're learning the functional groups for the first time. You're learning stereochemistry terms for the first time. It's just like, OChem 1 is so broad. The ABCs of the language, learning how to read and write. And then OChem 2 is just essay, 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 you know? It's just reactions all over. Although I have seen a lot of people that do well in OChem 1 and OChem 2. So I would say more, it's not so much that it matters what your strengths are, but who you're learning it from can make a big difference. How it's laid out, how you're tested, how well the tests match your learning experience, and how hard they want it to be. Now, I've seen some professors that just go stupid hard. And I don't know the benefit of it. Most students that take organic chemistry do not become organic chemists. I became an organic chemist. I went to grad school and I was in an organic division. I was one of 8 students that were organic in my 40-person cohort. And I wasn't very good at OChem. I had to relearn it in grad school. And I think it's because I wasn't that good at it, I didn't have a strong understanding, that I have developed ways to have a strong understanding. Practice, taking new angles at it, teaching. If you can teach it to somebody else, then you understand it. Nicole's got it. And I know that's hard, but if you make study groups here, then you can take turns trying to teach a concept. Go on a blank slate and just teach. Start small. Assume that they already know conformations. Teach how steric strain shows up in gauche conformations. I have to teach all of it. But you can pick just one aspect. Teach it to somebody in your study group. Have them teach you steric strain and eclipse conformations. Have somebody else teach steric strain and cyclohexanes, Teaching really gets it down. It helps when you get paid for it. But it is one of the most effective ways to learn something. Very different. They're almost not the same class, the same science. And it's funny, some people call general chemistry intro in organic chemistry. But in Gen Chem, you learn a little bit about organic compounds. You just there's too much to talk about with organic compounds. They're not like anything else. Most of them are tetrahedral, trigonal planar, linear. Whereas inorganic compounds can be trigonal bipyramidal, square bipyramidal, square planar, octahedral. Like there's so many more shapes that show up in inorganic chemistry that you never talk about in Gen Chem. But you can also make these enormous single molecules in OChem that you can't make in Gen Chem or inorganic chemistry. So they are totally different beasts. I actually love OChem because I struggled at it. I found joy in the challenge of trying to understand it better. Now I find joy in finding the challenge and getting you to understand it better. Okay. Questions on Newman projections and their energy strains?
I was reading in a textbook that they were having, like, wanting you to calculate, you know, I mean, is that pretty like, will we need to do that, or?
Great segue.
No.
Larger strain has, larger size has larger strain. I'm not going to ask you all to know the energy strains by numbers. You won't really have to do much calculations in this class at all. I'm not asking you to know their energy strains by number, but I am asking you to relatively rank their strains. So we're going to say, and I don't know, maybe I'll get cursed on the internet for saying this. That's okay. For the purposes of our class, we can say that a methyl group is about equivalent to an alcohol or to a halogen. And I know that's weird because the halogens are not all the same sizes. We say that fluorine is very small, but iodine is very large. I was actually looking at my Gen Chem textbook, the Real Chem textbook, and it was showing the relative atomic sizes of the elements. I was surprised by how similar in size they showed all of the halogens. That's not how I assumed it at all. I don't know if that was just on a particular scale that they were showing or what. But we can say that these groups all experience about the same strain. But what has a larger strain is ethyl. We can abbreviate ethyl ET. If you're not comfortable with that, you can call it, and I have my symbol wrong, I'm sorry. Those are less than ethyl. And remember, ethyl is CH2CH3. Ethyl is less than propyl, although it's much more common that we look at isopropyl. And remember, isopropyl is that Y. That's a CH3 2 coming off of one carbon. More groups, more size, more strain. And what's larger than isopropyl? Butyl. One of the most common butyl segments that we're going to use, tert butyl. It's that most substituted type. So we abbreviate that with TBU. That's carbon with 3 CH3s attached to it, or the chicken foot as it kind of looks. Ethyl, isopropyl, tert butyl. The largest strain that you're going to see all semester long always comes from tert butyl. If there's a tert butyl group, it's got a longer chain, a larger strain. But then you can kind of approximate. Longer chain, larger strain. So I want to take an example with you guys that makes this feel a little bit more real world. You know, I almost always teach about the conformations of ethane, which only has 2 different conformations, and then the conformations of butane, which has 4 very unique ones. But you can read that in the textbook. I want to apply a molecule with you guys. I want to look at phenylalanine. Anybody know what phenylalanine is? I think you'll know it when I show it. It's an amino acid. Alanine is this guy with a CH3 on the end. Phenylalanine has a benzene group attached. I want us to draw all of the conformations, all 6, for phenylalanine, starting from the conformation that we see. Looking down this carbon bond. Are you okay with that? So here's how I want to do it. I'm going to keep the front carbon unchanging, and we're only going to rotate the back carbon. Is this eclipsed or conformation, eclipsed or staggered conformation as it is? This is staggered because it's zigzag. And zigzag, staggered, is always more stable than zig-zig, which is why all of our bond lines are always zigzag structures, because it's staggered and it's less energy. So I'm going to start with a staggered conformation. I'm going to rotate to an eclipsed conformation. Notice that I'm only going to rotate the back carbon. The front carbon keeps its upside down Y. Then I'm going to rotate again, keeping the front carbon the same, and I'll get back to a staggered conformation. And then coming down, I'll do another switch back to eclipsed, another rotation back to staggered, and one last rotation back to eclipsed. And if I've done this right, then all of these just feed into this endless chaotic loop that the molecule can continuously rotate around. Now here's one nice thing. Because I'm keeping the front carbon the same, I can add in those groups throughout all of the structures, all at the start. What group goes here at the top? No. This is, yeah, that would be on the bottom. This is the front carbon, so it's either H, amine, or carboxylic acid. Carboxylic acid goes straight up. Amine is coming out to the left. Hydrogen is going back to the right. Carboxylic acid, I'm going to abbreviate that with CO2H. Grab onto my NH2. It goes to the left. Carbon, NH2. On the right is hydrogen. I'm abbreviating the carboxylic acid. Makes it a lot easier to draw it out. CO2H, CO2H, CO2H. If you don't want to draw all of these out now and you want to do this as exercise when you get home, go for it. None of this is changing. It's all in the same spot through all 6 of these conformations. That is kind of on purpose because the back is just fewer things to draw. So it's easier to rotate around. I'm going to switch to a different color to show what's on the back carbon so that it pops a little bit more for you. In my first conformation, top left, what is coming straight down off the back carbon? Benzene, the aromatic ring. pH. What is coming up to the right and to the left? What is coming up to the left and up to the right? Hydrogens. They're assumed, but they're there. H and H. We have a choice right now. We can rotate the back carbon clockwise every time or counterclockwise every time. It does not matter. Molecules can spin any way they want. Any preference? Then let's spin clockwise. pH rotates clockwise. This is not 120 degrees. This is just 60 degrees. If you're trying to pay attention with your models, this is going from the very first staggered, just 60 degrees, to the very first eclipsed. pH moves here. H, that's my bad. I forgot my H up here. Rotate another 60 degrees. Where does pH go? Top left. H. Yeah, take this, rotate it just 60 degrees. Tracking so far? Where is pH in the next conformation? Straight up, down to the left, or down to the right? Straight up. Rotate just 60 degrees. pH is straight up. Down to the right, down to the left. Where is it in the next? Up to the right. And then the last one. Down to the right. Are you tracking? Yeah? Little switches every time. We're showing each and every rotation. What does it do if I do one last 60-degree rotation? Starts over. All right, I'm going to label these as 1 through 6. Can you tell me the highest energy? Can you narrow it down to the 3 highest? What are the 3 highest? Good. So what numbers?
Oh, 2, 4, and 6.
2, 4, and 6 are going to be at the highest. 1, 3, and 5 are going to be at the lowest. Anybody disagree? Dylan.
2, 4, 6 on the highest energy? Is that what you're saying?
Yes. 2, 4, 6 will be the 3 highest. 1, 3, 5 will be the 3 lowest conformations. What do those have in common? You want to say it again, Will?
They're eclipsed.
These are all eclipsed. That's why they're the highest energies. Do you notice how every other is eclipse staggered, eclipse staggered, eclipse staggered? Take your model and rotate 60 degrees, eclipse staggered, eclipse staggered. You draw it out like I did before. You go up, down, peak, trough, peak, trough. All right, let's zoom in on 2, 4, and 6. Which of them has the highest energy of it, of the 3? Sorry? Four? There's steric strain between benzene and the carboxylic acid. No steric strain here, no steric strain here. How does that compare to 2? Steric strain between benzene and the amine. No steric strain here, no steric strain here. They both have 1 steric strain. You agree? The only steric strain that will result is where the benzene is. The hydrogens won't cause steric strain, not appreciable steric strain. So how do we rank the NH2? Yeah?
Doesn't the carboxylic acid and the benzene ring still have a steric strain because the benzene ring is on the back and carboxylic acid is on the front?
Here.
Yeah.
Here it's eclipsed with the amine. So it's not gauche,
Oh, okay.
because gauche is only staggered. Good question. You had the same point?
Yeah, I was gonna ask the same thing.
Good. Can't be gauche here. Has to be eclipse sterics. Good question.
Does the size of the groups matter here in terms of ranking them in any meaningful way?
Yes. We're going to have to compare NH2 to CO2H. What do you think? Which is bigger? CO2H. Remember I said longer chain, larger strain? Well, here's nitrogen to hydrogen, and here's carbon to oxygen to hydrogen. That's a longer chain. It's got more atoms in it. So that's going to be more strain. Carboxylic acid will cause more strain here than this amine. So our highest energy is 4. That's the wrong way. 4 is higher energy than, what's the second highest? 2. Why is 6 the lowest energy of the eclipse? There's no steric strain. It's only torsional strain. Because all eclipsed conformations experience torsional strain. And torsional strain is more powerful than steric strain. No steric strains because of H. No steric strains because of hydrogen. No steric strains because of hydrogen. All of them have hydrogen. No steric strains. That's our middle point. Now let's rank 1, 3, and 5. What's the lowest energy or the highest energy of 1, 3, and 5?
I'd say the highest of the 3 staggered ones is probably, I'd argue 3 because we got the 3 big molecules like all on one side over here.
3 big groups, to
Yeah,
be fair.
sorry.
But good,
I
good.
keep using the wrong terminology.
Yeah. Where do you find the most steric strain? Here, how much steric strain? Just 1. This doesn't count, doesn't count, doesn't count, doesn't count, doesn't count. What steric strain do you have here? Just 1. Hydrogens don't cause any steric strain. What do you have here? Phenyl to the carboxylic acid, phenyl to the amine. 2 sets of steric strain. So 3 is higher energy. Then 5, where the pH is gauche to the carboxylic acid. That's higher energy than being gauche, to the amine. Which is the bigger group, amine or carboxylic acid? Larger chain, larger strain. Carboxylic acid causes more steric strain. Amine causes less. Great work, guys. Is it clicking? These molecules experience a lot of stuff as they rotate. And sometimes specific conformations are required for specific things to happen, which means you need to be able to get that molecule to that energy level in order for it to happen. Sometimes that's easy, sometimes that's hard. Now, that's all fine for linear chains. We're going to have to spend some more time on Monday talking about rings, which means I get to push section 4 homework back even more. Because I can't do it in 4 minutes. I try. I'm not going to. First, there's this thing called ring strain, also called angle strain. This happens in our small molecules. Cyclopropyl rings, cyclobutyl rings, cyclopentyl rings. These angles are all less than 109.5 degrees, which is the preferred tetrahedral bond angle. So these molecules experience intrinsic strain from that. Cyclohexane is perfect. Okay, it may not be perfect, but it is incredibly stable.
Is this why everything's hexagons?
This is why if you buy organic chemistry notebook for a class like this, they often have that hexagon grid pattern. Hexagons or bestigons. What is the shape of that cyclohexane? How does it take up space? Flat? Looks flat, right? There it is. Flat. You agree? You don't agree? There is something weird going on, right? Like, there's an H here, but not an H here. Here, but not here. Here, but not here. This alternating pattern going on. And you can actually kind of get a sneak peek. Oh, the H is down there, but it looks flat. You guys seen this before? It's a zigzag. I'm not lying. It is a zigzag all the way around because zigzag is staggered and staggered is lowest energy. This is cyclohexane in its lowest energy conformation. Here is cyclohexane in its highest energy conformation. Flat. No, I'm just kidding. It's eclipsed. Kind of. It's a different kind of eclipse. But it's got all of this steric strain that's going on. It even has some torsional strain in there too. These are the two main conformations of cyclohexane. And this is where we're gonna spend time. Cyclohexane can go from its first chair conformation, which is basically a staggered conformation. It equates to being the staggered conformation of a linear chain. And then it goes through a boat conformation before it can relax into its second chair conformation. This is like going through an eclipsed conformation, just like on a linear chain. But unlike linear chains, which we saw can just go around and around and around and around, chairs are locked. This is it. These are their two conformations, chair and boat. You'll actually see there's something called a twist boat, which is halfway in between the chair and the boat. We're not going to look at the boat. We're not going to look at the chair boat. We're going to look at just the chairs. And we're going to get to know those two conformations that the chairs can take on. There's a lot of information that goes into these. I think the last thing that I want to leave you with on these chairs, no, I think that's pretty much it. Wait, it's going to take too much time. I'll let you guys out on 2 minutes early. I'm a nice guy like that. Have a good weekend. We're going to dive into chairs on Monday. I'm hoping to spend an hour on them. No more. I thought I'd spend an hour on them today, but that didn't happen. And then we're going to move into section 5, which is about chirality. And we've got some fun things to talk about in section 5 Monday and Wednesday before your unit test at the end of next week. All right? Have a great weekend.